Energy Initiative, and also Deputy Director of the MIT Joint Program on the Science and Policy of Global Change. He's the lead modeler in charge of the MIT Economic Projection and Policy Analysis Model of the World Economy. Dr. Paltsev is author of more than 100 peer-reviewed publications in scientific journals and books in the area of, actually in the diverse area of energy economics, climate policy, taxation, advanced energy technologies, and international trade. Sergey was a lead author of the fifth assessment report known as AR5 of the Intergovernmental Panel on Climate Change known as IPCC. He's a recipient of the 2012 Pike Johnson Award by the Transportation Research Board of the US National Academies for the best paper in the area of planning and environment. For more information, please do visit his webpage at MIT. And the title of his talk today is about hard-to-abate sectors, the role of industrial carbon capture and storage in emission mitigation. Sergey, thank you very much for accepting the invitation. The stage is yours.
Well, thank you very much for this kind introduction. I'm very pleased to participate in your event. I think, that's an extremely important and extremely timely event. So let me start with trying to share my screen. So let me know if you can see the slides. Okay.
Pretty well, yes, please.
Thank you. Okay, so what I'm going to do in the next 25-30 minutes, I'll try to provide a big picture. Obviously, I won't be able to go to all the details of issues related to the industrial carbon capture and storage, but hopefully I will provide you, the main things in terms of the opportunities and also challenges which are related to industrial CCS. I'm also going to provide you the links and contact information. So if you are going to have any questions, I know the time is going to be short, so feel free to contact me or feel free to visit our website, and we will be more than happy to continue the conversation. And well, that's one of our objectives here for this meeting, is to make sure that we find good questions, good collaborations, and hopefully we also are going to inform you about this topic and our activities related to this topic. So don't hesitate to ask any questions, don't hesitate to contact after the presentation. I'll start with setting a big picture, just to remind the scale of the challenge and to remind the dynamics of the CO2 emissions. So what I put on this chart is the historic development of the fossil fuel carbon dioxide emissions from 1965 to 2019 is the last year in this figure. A couple of things to note. Well, one, we are increasing emissions, and we are increasing emission at quite a high rate. Point two, well, you may recall something like Kyoto Protocol, Copenhagen Accord, well, Paris Agreement. Well, all these are happening, but the emissions are still rising. So it means that, well, one immediate thing which comes to mind, that we need to do more. We need to do better in terms of the reduction of the emissions. Another point, you see that blip around 2008, so emissions going down. And also, well, in our current environment with the global pandemic, the current expectations that the emissions are also going to be lower by, well, different estimates are providing the number between 4 and 8%. If you're going to take a look at the historic precedent of 2008, so after the global financial crisis, after the short period of the reduction, if we went back basically to the previous trajectory. So the key question is, are we going to change that trajectory? Because definitely we are not on a sustainable path in terms of the emission reduction. So is it going to be only temporary reduction and then we are going back to business as usual? Or indeed we are going to try to change this trajectory and try to get into a very different path in terms of the emissions. Another point to make from this graph is if you're going to take a look at the 4 major regions, so I put here China, US, European Union, and India, well, that's already more than half of the global emissions. So that also gives you an indication that whatever the solution, whatever the policies, whatever the technologies we are going to employ, we need to make sure that these regions are leading that. And so these regions are really setting the stage, because if we can try to find the solutions for these particular regions, we already are going to get a majority of the problem, and hopefully we will have synergistic activities for other regions. So now to the industrial emissions. So the title is Industrial CCS. We are doing CCS, carbon capture and storage, in power generation, and it's a lot of the experience with that. Some more successful, some not, less successful. So, but it's even more important to find the solution for industrial emissions. And one key feature of the industrial sector is that it's not only emissions that are related to combustion. So you can see that those emissions are about 20% of the global CO2 emissions, but also so-called process emissions, so process-related emissions, which are not related to combustion, but related to the processes, so like in cement process, in iron and steel, and so on. You have the emissions in petrochemicals. You have the emissions where you're using fossil fuels not for combusting, but you're using fossil fuels in order to convert to other products. And so it means that, well, you need to find the solution not only for heating purposes and other purposes which you're using your energy for combustion, but also for those processes which are not related to the combustion. And that makes it even more challenging for these sectors. And that's why these sectors are sometimes called hard to abate sectors. And so that's the name because it's much harder, it's much more expensive to remove emissions from these industrial activities. Another feature of this sector is that it's very heterogeneous. So it's not just one output like in power generation where we are producing electricity and heat. Here, well, we have many processes, and those processes may be very different even in one industry if you are talking about different regions. So again, the solutions are going to be more challenging in comparison to, let's say, with the power generation. I put this slide is to just contrast where we have been historically with where we need to be. So these are probably very familiar picture for you who are following the climate change related policy. So this is from the recent, relatively recent at this point, IPCC 1.5 report. And these are 4 different trajectories for the emission reduction. And obviously it's a lot of uncertainty, a lot of scenarios, and what is the role of, for example, forestry, agricultural forestry, and other land use emissions, AFOLU, biomass with CCS, BECS. But regardless of that, the message is clear. By mid-century, we need to be at about 0. So if we are really seriously taking this into the account, it means that we need to change the trajectory of the emissions quite dramatically. So let's take a look one more time. So this figure combines the previous figure for historic trajectory for global CO2 with the needed reduction which we need to get to those 2 targets. So a couple of things which I want to bring to your attention is, well, one, no matter what if we are at the higher range or low range in terms of the required emissions, we will have to do that at a very unprecedented rate. We would need to reduce emissions at the rate much higher in comparison to how we were increasing emissions. And well, you can judge by yourself about the realism of those trajectories, but that's what is needed for 1.5. At least that's what scientists are telling us where we need to be. And again, I already made that point where I have compared the temporary reduction in emissions due to financial crisis, the global financial crisis. And also, well, our current reduction estimate for 4 to 8% in 2020, and the big question mark, how we are going to get out of the pandemic. What would be the new trajectory? Are we going to have structural changes? Are we going to have packages to support the decarbonization? And it's not only about CO2 and it's not only about the industry. You're already seeing that 25% number, which is related to fossil emissions, but it's also other emissions which we need to remove. So agriculture, forestry, for example, in terms of greenhouse gases is a major component. Well, why this is important for industrial emissions? Because remember, zero emissions requirement, it means that we have to remove all these emissions to zero. So it means that either everybody has to be at zero or somebody is going to employ negative emission technology. And then it's going to be a lot of arguments, well, which sector is going to be allowed to have positive emission technology? Because, well, a lot of sectors will claim, oh, it's very hard to remove the emissions and we need to have the special treatment. So it means that we need to find the scalable low carbon energy options and scalable low carbon industrial CO2 emission reduction options. And why it's important? Because many governments, many companies, many jurisdictions are already announcing those net zero targets for 2050. So, for example, company like Dow Chemical, they said they're going to be net zero 2050. Many major oil and gas companies are making those announcements, and that means for them a really dramatic change in the business, what they are doing. And it's not only about the available technology, and indeed that's important, do we have the technologies to do that? But also about the economic competition. Who is going to win that race? Which regions? What kind of policies we need to support these technologies? Because, well, what we are going to do in order to decarbonize most likely is going to be more expensive. So it means that they need some kind of policy support for their deployment. A lot of things are going to be impacted by geopolitical considerations. So it's not only about the economics, it's not only about the technology, but well, there are many other goals for the society. So like reduction in poverty, reducing income inequality, public safety issues, health safety issues. So all these goals has to be done in conjunction with the decarbonization goals. And currently, in the global pandemic, we are actually moving to the situation where we are going to have a rise to more and more protection. So it means that the supply chains need to be also addressed in such a way that if next time we are going to have something like that and we have a risk of closing the borders, that you are not affecting your supply chain. So that's extremely important. And whatever we are going to create needs to make sure that we are fulfilling the environmental objectives as stated. So these two diagrams from the latest IEA World Energy Outlook, these are the pre-COVID scenarios. Well, obviously all energy projecting agencies, including us who are also producing this type of scenarios and projections, well, now we are trying to understand, well, how the pandemic is going to affect all these trajectories. Is it going to be short-time implications, or it's going to be change in the long-time trends? Well, one point from this diagram to show you that, well, by 2040, we are not going to decarbonize industry. So in 20 years or 2 decades, we still are going to use coal and natural gas, sizable amount of electricity. So it means that, well, if we decarbonize electricity, which seems to be a little bit easier task, then we are already doing a lot in terms of the decarbonizing the energy which is used in the industry. A lot of considerations which needs to be added to the question of just, do we have the right technology? Because, well, it is a lot of changes which might happen, how we are getting out of the pandemic, how we are going to change our activities, because that is going to also change the demand for certain products. So it means that you may have some effect on the industrial sectors in terms of, well, what would be required, what would be the new demand, what would be the changes in the current trajectories. I already have made this point that if we are prioritizing resilience of the efficiency, it means that we are going to have less efficient system. It means that we need to change to decarbonized area with much more challenging situation. Well, that's exactly what we do at our Energy at Scale Center. So I'm directing this center at MIT. And again, I'm not going to have time to go over all the details, what we are doing in terms of scaling up low carbon energy, including the industrial energy. But I have provided this link so you can go ahead and explore the topics and you will see that we are covering the quite broad areas of different topics. So we are employing very well-established tools which are related not only to the energy, not only to the industrial sector, but also connections to the Earth system. And so we are looking and trying to understand immediately what are the implications of different technologies, what are the implications of different policies. And we are doing that in the integrative manner because we are capturing the whole globe, whole economy, and we are capturing all the interactions between all these sectors. And well, this is quite elaborated tool. And again, if you have any additional questions, I advise you either to contact us or follow up with our website. So now to the topic of decarbonizing options for industry. So I'll elaborate on that very, very briefly. What are we trying to look at? Obviously, we are trying to look at many options, and that's what we are trying to understand. What are the options, for example, for new materials, for improvement in efficiency, for electrification, for carbon capture, for hydrogen. Again, the disclaimer that, well, hydrogen is only as clean as the carbon, as the source from which it was produced. So it means that it needs to be produced from, let's say, steam methane reforming with CCS or through electrolysis, use of biofuels. And so our approach, because I already mentioned the wide diversity of the processes, currently we are focusing on something what we call a marker industry. So we are trying to understand, well, what are the options in cement? What are the options in iron and steel? What are the options in chemicals, in refineries? And I already mentioned that another important consideration is what is the future of for the fuels when they're used as energy inputs versus feedstock inputs? Because if you are using that as a feedstock inputs, well, at least in some cases, you actually not releasing carbon. So that might be another avenue to move to the products for fossil fuels and move away from combustion uses to the feedstock uses. And so we are exploring what is the potential for that. So I'll briefly go this industry by industry. I'll provide you just a couple examples. Again, I know that I'm not going to have time to go to all the details, but hopefully that is going to give you the picture of the challenges, at least in a couple industries, and where we see the potential solutions. So I'm showing you here the emission implications from different ways of producing steel. And immediately you can see that those emission implications are quite different. So if you go the traditional route, blast furnace, basic organic furnace, versus if you are going to do the electric arc, and especially if you are doing electric arc with zero carbon electricity, well, the implications are quite dramatic. Well, again, we need to understand what is the relative economics. And so that's exactly what we are doing. Because if we are talking about the electric arc, you can produce that steel from scrap, or you need to use some other processes like direct reduced iron. And so then the combination is actually a little bit more carbon intensive. And currently, majority of the steel is still produced the traditional way. So it means that the majority of steel production is very carbon intensive. And again, it is mostly affected and dominated by the way how it is produced in China, where majority of the steel is still used coal and used the traditional way. But in many places, the direct reduced iron is also very prominent. So for example, almost half of the steel in India actually is used produced through direct reduced iron process. The only thing that in many places that route use natural gas, but for example, in India, they use coal for this production process. And again, the ways for capitalizing the fuel substitutions are extremely important to understand. Well, already there are some examples of the CCS on steel production. So Abu Dhabi commercial plant is already up and running since 2016. And that's the first commercial facility. And they are using the capture which they are getting from the DRI reactor. And that CO2 is transported by pipeline for enhanced oil recovery. Again, that's the critical piece to make sure the economics is working. Because if there is no support, well, the economics is not going to be favorable if you are not going to have other policies. Other innovative steelmaking processes. So for example, Tata Steel is looking very hard, and they already have many successes in promoting their Haisarna process, which is producing flue gas with very high CO2 concentration, so which is very attractive for carbon capture and storage. For example, the Swedish steelmaking company made the announcement that they have done a very successful test where they use hydrogen for high temperature heat. So, well, only in the part of the steel making, so it's not the full process, but still that's a very promising avenue to go to hydrogen-based steel making. Now, in terms of the cement production, well, that's actually about 10% of the global emissions, the whole cement industry, and half of that is coming from fuel combustion, half of that is coming from the process. The problem with trying to decarbonize cement production is that in most of the current options for CCS, we need steam. So for that amine process, well, we need steam, and there is no steam in the cement production. And so as a result, we need to add that steam facility in order to capture, in order to run the stripper and absorber. So that's exactly what we are trying to understand. What are the processes? And so this is the illustration of the amine-based post-combustion capture, which captures up to 90% of the emissions from carbon plant. And again, we need steam for regeneration of the solvent. And again, that adds, so that top area on this figure, well, that's the capital, that's the equipment which you need to add to cement plant. And again, that's the question of the economics. How feasible is that? How competitive you are going to be? And again, that calls for need for the policies. We also look at more advanced ways. So like in the power generation, it's net power, Allen cycle, for example. Here we are looking at the cryogenic carbon capture, where you don't really need the steam because you only need electricity, so no additional fuels are needed. And while there are some testing of this technology, and again, you can go to the website of the company which is working on that. And so that's another innovative way where we can find the solutions to the problem in the advanced research and try to understand, well, what would be the economic implications if this R&D is going to be successful. And this graph shows you those economic implications. So we have done the estimates, what would be the cost in terms of ton of CO2 avoided if you are going to use cement with post-combustion coal or post-combustion natural gas. And you see those big blue areas, and these blue areas is additional capital, additional equipment. And so that's what makes it so expensive. While the cryogenic way, you need much less capital. That doesn't require, you don't need to build those boilers for steam production. So the cost of electricity and use of electricity is bigger, but in principle, while that might be much more economic way, again, we still need to do a lot of testing and demonstration for this technology, but that gives you the scale of the potential cost reductions in all these different avenues. Very briefly, well, that actually changes the picture dramatically. If we have CCS or if we don't have CCS, well, that affects the way how the output of those energy intensive industries are going to evolve over time. And you see these big areas where the economics is pushing the CCS quite a big way. Otherwise, we will have substantial impact on the demand of these industries. And again, the cost of reaching these targets is also quite different. So you can meet exactly the same target if you don't have the options like CCS. The cost of that is going to be dramatically higher in many, many cases. And again, here for illustration, we have made quite dramatic assumption that CCS is the only option for industrial decarbonization, just to test what that would be. And you can see that while 20–30% increases in cost of meeting the same target, in some cases it rises almost to 70% increase in cost. So it means that if we solve that, we can decarbonize much cheaper. Also, these diagrams showing you, well, that dark blue color, well, that's the energy intensive industry, that's the hard to abate sectors. And while we are decarbonizing by 2100, so not by 2050 in these particular scenarios, but you can see that while those blue color is the one which kind of dominates. So it means that indeed in our assessment of all the sectors in the economy, which are listed here, the industrial emissions are hardest to abate. It means that we need to find the solutions for this sector. So a couple of the concluding thoughts that we need broad range of technologies and policies. So we looked at many combinations at the renewables, wind, solar, hydrogen, CCS, nuclear, and we find that there is no single technology which is going to solve the decarbonization challenge. So it means that we need to look at many pathways and we need to employ that differently in different parts of the world. We also find that whatever option which might work better for, let's say, China, may be different for what is going to work better for India or for Africa or for Brazil. So it means that we also need this region-specific understanding, region-specific studies. Another point, zero means zero. So sooner or later, we need to decarbonize. And it means that the engineers, the policymakers, the industrial leaders need to work hard on the strategies. How do we get there? Because that is going to be a requirement, ultimate requirement. Public acceptance, extremely important. Policy support, extremely important. A lot of these options are going to be not so cheap. So it means that we need to find a way how to support them. And solutions for scaling up needs to work not just in one particular sector. So it means that if we are looking at, for example, hydrogen or CCS, well, that's more advantageous because that potentially can lead to a lot of synergies to decarbonize other sectors. Another point which we are making often in our presentation, while we want much more aggressive targets, there is nothing magic about 2050. There is nothing magical in the 1.5 or even 2 degree. So what really is needed is making sure that we are reducing emission as dramatically as possible. But it's not the end of the world. So hopefully it's not the end of the world, at least our current understanding, it's not the end of the world. But we need to make sure that we are changing that trajectory. And we are not giving up saying, oh, well, no, it's unrealistic. We won't be able to reduce that fast. Well, we need to try. So again, well, there is a good phrase, we need to shoot for the stars and maybe we'll land on the moon. So, well, if that's the case, well, that's also good. So we need to try as hard as possible to find these solutions. And another obvious conclusion from the academic institutions like MIT, we need more research. Obviously, we need to understand more of this. And that's exactly what this conference, exactly what this symposium is doing, is creating the knowledge, making sure that we are looking for the answers together. And so that's the last point which I was trying to make during my presentation. Again, thank you for your attention. I'm more than happy to go to Q&A, but before that, I hope that you all safe and healthy, and I wish you that, well, we will have a fast recovery from where we now. And again, thank you very much for your attention.
Thank you very much, Sergey, for this very comprehensive and interesting talk. I would like to also remind the audience, please do feel most welcome to text your questions in the chat room or Q&A panel, whichever you find convenient. We have received a question already here, and I would like to just read it for you, Sergey, and in the remaining 6 minutes that we have, we would like to just have your feedback about. But I would also like to inform audience, please do feel most welcome to contact him later also about any questions, especially for the MIT at Scale Center collaboration. So we have a question actually from China, and that's the question the colleague is asking about. The global warming is partly due to the greenhouse gas emissions and partly about the use of other resources of energy and heating up and inefficient systems, like the use of other fuels that would be creating heat and not necessarily greenhouse gas emission. And a comprehensive or integrated look at this problem would perhaps also be willing to include those aspects. Would you comment on that?
Yeah, no, I fully agree. Decarbonizing heat is extremely important. And it's also, I understand why that's a question from China, because it's a lot of centralized heat. So in several countries, whenever you're running, for example, coal power plant, you're not running that only for the purposes of producing power generation, but also for the heat purposes. And so as a result, the dispatch of these power plants may be very, very different if you're just in the power generation business, because you need to provide that heat. And so that's much more challenging because you need to address these issues which are related to heat generation. And definitely that's probably one of the most important challenge in this area, how to find the solution for decarbonizing heat, because it's very, very challenging. And again, I already hinted at some of these. So again, use of CCS or hydrogen. So that's another option. Absolutely. There are a lot of research on electrifying heat. So I fully agree with that statement.
Thanks a lot. We have another question from Sarah. She's asking about your research outcome and the findings about different cost in different industries for CCS. Obviously, some industries are a bit more, everybody's equal, but some are more equal. What is the heterogeneity of the cost of CCS in the industry?
Right. So That's another very important challenge, but also a very good opportunity to understand what are the options, because as Sarah correctly noted, the cost of employing CCS is going to be different. The cost of employing CCS is going to be different even within the industry, because there are different technological options. So I gave you, for example, some numbers which are related to steel making. There are many processes. So it means that if you are trying to employ CCS, let's say on the blast furnace versus on the direct reduced iron reactor, well, that's already different approaches, different costs, and different capture rates which you are going to employ, and where that carbon is coming from the steelmaking facility also matter. And so if I would rank like industry by industry, where it's more challenging, less challenging, I would say that we know much more about the power generation. So there are a couple of the plants which are already up and running, not in the demonstration mode, but at the commercial scale. So we know the cost, we know the performance, we kind of more or less understand what it would take. And again, there are a couple of very promising pathways. It's on cement industry, again, well, so the cost is going to be dependent on, well, what is the concentration of CO2 in the flue gas? So I give, for example of high Sarna technology, where you have 90% concentration. It's much easier to capture. Right. And how distributed the CO2 in your process. So for example, if you are going to take a look at refineries, there are many places where that CO2 is coming out, versus if you have the process where everything comes out of the same process, where all CO2 is coming from, again, combustion or something, the heater. So that is going to be determined relative cost at this point. And so if you have the industry where you can combine and increase the concentration of CO2, the cost is going to be lower. So power generation, cement. If you have more complicated processes, petrochemicals, other things, that's going to increase the cost.
I see. Capture remains to be a key factor here.
Exactly.
So I have some more questions. I would like to just read one of them, and I would apologize to all others who might have questions, but because of the timing, I cannot read every question. We have a question from Emenak. I hope that I read the name also properly. It's about two options that we have. We have centralization systems, decentralization systems. Do we have an optimum situation in which we would like to decide where to centralize, where to decentralize, and what would you?
That's another very topical and very important question. And for the sake of time, I'm not going to go into too many details other than stating, yes, we need to find that optimal solution. And in the power generation, that's exactly where we are trying to understand, well, where you have these decentralized grids, how to make sure that you're supporting the, for example, intermittent renewables in the best way, versus where you have the centralized facility which produces electric power. So again, I'll be more than happy to follow up. I don't want to penalize the next speaker capturing his time. So again, thank you very much. These are great questions.
Thank you, Sergey. And I would like to thank you once more, and also the audience for the great questions. Please do contact him for further discussions. I see a lot of topics that are quite important, and Sergey is also very much willing to get engaged with you about it. Thanks once more. I would like to